Okay, so now I think we are ready to start with our first invited speaker talk. Bram Vanderborght is a professor at the Vrije Universiteit Brussels in Belgium. He's a member of Robotics, a multidisciplinary research center on human-robot interaction in Brussels. And he also co-led the Homo Roboticus project on how to keep human values central in a robotized world. His main research interests include the use of soft and self-healing actuators for cognitive and physical human-robot interaction in applications in health and manufacturing. So Bram, I see that you already shared your screen.
Yes.
So I think you can start your talk. It's you have 25 minutes, and then afterwards we have 5 minutes for questions and answers.
Yes, thank you for the introduction and the invitation. So I will talk about towards Industry 5.0 with collaborative robots. So the classical robots are used for the 3D jobs, dirty, dangerous, and difficult and dull. But some say that it will be also for becoming a 4D story, where demographics becomes an important player. We see that the average age is increasing. We need to work longer. And this is the case in Japan, but also China, due to their one-child policy, but also in other regions like Europe and so on, this has become a serious problem. Moreover, the complexity of manufacturing is increasing a lot, and typically robots are taught to manufacture cars, which is certainly a large part, but it's also not the complete story. And so you have a wide range of series, and as a customer, you have a wide range of possibilities. So every car is almost becoming unique. And so in the beginning, when you have the body shop, you don't have a lot of variation. You have 3 doors, 5 doors, the paint also too dangerous. So there is a very high level of automatization, but in the end assembly, where all the different variations become flexible parts, and we see that the level of variation increases, but the automatization dramatically decreases. For example, in Audi Brussels, at the moment when they were producing the A1, there were 5 robots active in the end assembly. All the other jobs were done by humans who have to have the cognitive load, but also they have to work with their hands above their head, bend over in the car, which causes troubles on their musculoskeletal disorders. And for example, Elon Musk also expressed it that they wanted to make it too automated and that humans are underrated. But all those work in non-ergonomic conditions has a huge impact on the body with lower back pains and other pains, but it also has a huge economical impact. And for example, in Belgium, it costs €1,000 a day for one person being absent. So if you have a few percentage of absenteeism in your work floor, that has a huge impact on the productivity of the plant as well. And so that why then not use robots? But there is that famous paradox in robotics that often what is very challenging for humans is easy for humans, but also often what is challenging for humans, like working very precise, doing always the same job, doesn't become tired, is rather easy for robots. That's why we focus a lot in our lab on human-robot interaction to exploit the complementary strengths between humans and robots. And also, the human is for us still a huge source of inspiration to build better robots. And so Industry 5.0, in the past, objects were built for the elite at a very high price. And due to the several levels of revolutions, industrial revolutions, we could produce mass products. For example, the famous Model T of Ford could be get in all colors as long as they were black. But the idea of the fifth wave is to have mass customization. I, for example, run in the forest in the morning, someone else at lunch in the city center. We all have different feet. So how we can produce a shoe which is made individualized for a certain person. So that we cannot do with mass production, we need to do it locally. And to make that at the cost of mass production, but with the uniqueness of mass customization. So we need new technologies like robots or others like 3D printing in order to realize this vision. And for example, Adidas developed its first factory outside China back in Germany, the mother country, but they also had to close it again, probably because the technology was not ready. And so, as mentioned in the introduction, safety is of course the primary concern if we want robots to be working together with humans. And so here you see the classical industrial robots being crushing a coconut, a video of DLR, because it's too unsafe, and that's also the reason why those robots are kept in cages far away from humans. And so 15 years ago, I think, we started innovating this with a lot of projects like fire actors and others, developing robots that are not position controlled, but torque controlled, and which have the possibility to interact safely with humans. So we in our lab focused a lot on having the compliance not by active control, with torque control, but incorporating elastic elements in the parts so that it's not only safe, but we also want to work on energy efficiency. And for example, we developed it for our prosthetic feet, which is now a spin-off company, Axelis Bionics, of our lab. So we introduce springs in parallel in series, but we also are further investigating how we can make designs of the robots to be, on one hand, safer, lighter, more energy efficient, so they can also be mounted on ground vehicles. So for example, we introduced, and that was also part of the work of Kelly, had to make flexible limbs, that we don't design robots on strength anymore, on stiffness anymore, but on strength, so we could reduce the mass of it, and that also improves safety. We're innovating on new gearboxes, so this is also patented technology. We also want to go to a spin-off there to make the gearboxes much more energy efficient, because we see a lot of energy is lost over there. We are investigating if we can have remote activation, so the distal joints of the arms, but also of the exoskeletons, are lighter and as such more energy efficient. And we're also seeing ways to add more motors so that the overall system can become more energy efficient, a bit inspired by hybrid cars, where you have a combustion engine and electric engine, but the overall system we want to make more energy efficient. So this is how to make hardware for improved human-robot collaboration. But of course, we want to avoid that robots hit persons, and this is a very nice work of Kelly, where we want, of course, to avoid that a robot hits a person while taking all the constraints into account. So typically, model predictive control is taken there, but she developed together with her co-workers from Boulder University as well, is explicit reference governor, which can be calculated in real time while taking, here you see that she placed extra mass on the robot so that she pushes to the torque limits, but you still see that those constraints of torque and speed are satisfied. And she made it that the robot tries to follow this blade with 30 centimeters on top, so to show that it's real time. And at the moment, she's wearing a motion capture system in order to determine the robot where she is compared to the robot. Of course, this is not practical in a real scenario. That's why she's now also using cameras, but also that has limitations. And that's why I recently also joined IMIC, which is a big research institute in Belgium on microelectronics, where we want to see how we can develop a new generation of sensors, of skins for robots, in order that we don't need these external systems anymore, but we can embed it on the system to detect where are obstacles, and that this sensing can be used combined with the control that, for example, Kelly developed. So at a certain moment, several years ago, Audi Brussels, at that moment building the Audi A1, approached us and they saw the development of the cobots and they wanted to test those cobots on the manufacturing floor. But when we entered the manufacturing floor, we saw that people got afraid of a new wave of robotization, while our story was, yeah, we want to reduce cognitively and physically your load. We want robots that help you. And so that's why we very quickly took the assistance of sociologists in the project in order to help us how we need to build and program robots so they're accepted by the workers. And that's why this robot, it's for a glue operation for a part in the body of the A1 to reinforce the roof for the racks of to put your bikes on the car, which was not done very precisely by humans. So that had to be done by robots. And so one of the features is that we start to experiment with also gestures. So you see that the worker can do gestures. And in order to respond to robots, there was also a face, but we have some copyright issues with the artist that designed the face. So that's why I'm not allowed to show it anymore. And so when the persons were in the start very afraid of this new technology, now they're really proud to work with the robot. It allowed a new wave of different cobots in the factory for very different applications. Now they're building the Audi e-tron electric vehicle. And so this was the robot, the only robot, and they have had 500 robots at that moment who got a nickname, for example. So it was really accepted by the workers. And so that was a whole new type of robot introduced there. Due to liability reasons, we were not allowed to let the human physically work together with the human, because there are issues on certification and certainly at that moment in the factory. So that's why we have at this moment workspace sharing, but no real collaborative working. Also, this was the only robot allowed at that moment by the Metal and Wood Union in Germany, which Audi Brussels took over their rules. But we continued to work where we saw how humans and robots can work together. And this is, for example, task allocation, where we distribute tasks between a human and a robot, both having different capabilities. Also, the human having having issues with ergonomics. So you see that we track the ergonomics of the worker and we distribute the work over the human and the robot. If we take another robot like Franka, who is much more precise, but only has one arm, you see the system automatically adapts a new task allocation scheme in order to optimize the work. Now we're also in a European project called Sophia, where also the idea is to improve ergonomics. And also here with the Kinect camera, we track the posture of the worker. If the worker goes to non-ergonomical postures, the screen becomes red and the robot adapts its behavior so that the human can always work in a more ergonomical place. Apart from always collaborating with cobots, we also want to very intuitively program the robot new behaviors. And I think Sylvain will go much more in depth there. And the reason is that we want to go to much smaller batch sizes in manufacturing, but then it becomes very expensive to program the robot. And yeah, then it's better to still use humans for it. So big companies like Audi Brussels can afford it, but what with small and medium-sized companies who don't have the programmers in-house to always reprogram, and then especially for small batch sizes. The problem is, of course, robots, we don't have, in this case, a lot of models, the models of the CAD models and so on, but not of how the assembly sequence should go. And leaving that all to the robot, for example, here we use reinforcement learning, yeah, that needs so many iterations yeah, that is not very practical to implement that, especially for small batch sizes. That's why Joris is investigating how we can use interactive reinforcement learning, like a teacher-student relationship, to guide the robot to do the assembly sequence, so the robot learns in a much faster time. Another approach Joris explores is to train in a digital twin. Hey, that's now a very fancy word for using simulators. One of the challenges is, of course, in an assembly sequence, the physics become important. For example, here you see it's touching it, but also placing parts around it. And so that's why he had to use engines which included all the physics in it in order to have a realistic training of the device. And so here we see different behaviors. So here on the right, it's only the video to show that the reality is quite equal with the physics. But what we do is we only train in the digital twin until we have a meaningful assembly sequence, avoiding all the errors. And then, of course, the simulator doesn't represent completely the reality, and we can still optimize in the real world. Like, for example, timings are not completely correct because we only simulate the end effector and not a complete robot in order to make it faster, the simulations. But then it can do different assemblies, but we still optimizing it to see how we can still save time and be a bit more productive. One thing is that we want flexible assembly, but we still see that robots have very limited capabilities. Of course, we have they're developing humanoids which can do a much more rich amount of tasks, but we see that, of course, those robots are very expensive. And that's why Brian Convent started to think, how can we not use multiple agents with different capabilities, and that for flexible assembly, they very dynamically come together in order to have the work done. And so to start that research, he also uses the explicit reference governor as the base, but in a different distributed fashion. And he started with small drones here, smart flies, also work performed at Wilder University, to make different agents have all going to different tasks to go different positions. And the idea is that every agent individually is saved, that so you don't need any communication, and the individual agents all handle their constraints. One thing to say is they don't do it on the perception side. That's why you see on the outer place still the motion capture system. And again, that's the reason also why we joined IMIC. So other researchers are now working in the team to do the perception task. Where are the others? Where am I? So we're working on ultra-wideband localization, on sensor fusion techniques to see different the other obstacles and so on. But the idea is, if we have communication, then the agents can exchange information, and you see that the swarm becomes denser, the distance traveled is less, smaller settling times, and so on. And now future work is how the different agents can also physically take loads, for example. And our vision is that drones, cobots, exoskeletons in the future will very dynamically come together. Tasks are distributed over different agents, depending on the individual needs of a certain task, which can change from task to task. And I think we need to get rid of chains in manufacturing plants, because, for example, we see it at Audi Brussels, a car with a lot of work or with a few amount of work, because it's all on the same chain, they block each other, which, while it can be done much more efficient when there are different agents dynamically coming together to do the job. But it requires a complete rethinking of the manufacturing plant. One extreme of cobots is wearing the cobot, and that is, of course, the wearable robots or the exoskeletons. So in our lab, we develop different exoskeletons where we implement strategies like locking mechanisms, parallel springs, and so on, in order to use very small motors, also have not very broad exoskeletons, because in a manufacturing plant, you need to be able to still navigate in a cluttered environment, going through doors and so on. So the device cannot be bulky. You need to be able to have your versatility of the human body. And for example, here you see exoskeletons for the upper limbs, as for example, to work under a car, while still having all the freedom to move the arms. So we have here patented solutions in order to have that complexity of the shoulder, still having all the freedom to move while having assistance in certain motions. And also here, it's not only a matter of developing technically the exoskeletons, but also investigating what is the impact of that technology on the human body. And we see a lot of exoskeletons appearing on the market, all claiming that they assist workers to do their job, but jobs come in a lot of diversity. And so companies like DEME, they make dredging on the sea, so they have to change the teeth, which are very heavy. A car glass, they change the windows in a car when they're broken, warehouses like our supermarkets. And so what our human physiologists do is they go to measure those motions at the workplace, reproduce them in the lab with all the physiological measurements, EMG, oxygen consumption, and so on, with the different exoskeletons, in order to investigate which exoskeleton is most suited for a certain job. And then also the same sociologists come in to investigate, are workers willing to wear the exoskeleton. For example, some exoskeletons put a lot of pressure on the chest, which is especially for women not very comfortable. Others, you need to take a long time to go to the toilet, for example, while you have a limited break. So you don't have just time to take it off and wear it again. So the donning and the doffing times are very long. Some have become very hot. And so we recently also published a paper. What is the framework of exoskeleton acceptance? What are all the aspects we need to take into account in order that the worker will accept such a technology? And so we hope it's a tool for designers of exoskeleton. What are all the aspects they need to take into account to see if a worker will accept the technology? One of the aspects is you saw that we use a lot of soft materials, especially springs, in the design of our robots, on one side for safety, but also for energy efficiency. One extreme is, of course, the use of complete soft materials, and that gave rise to the so-called soft robots, where also in manufacturing, but also, for example, in harvesting fruits, we see that those soft grippers become popular. But of course, they come with a price that those materials are vulnerable to damages from sharp objects, overloading, fatigue, also interfacial debonding. And for example, the Empire Robotics gripper, which is a very nice gripper that can grasp a wide variety of different objects, which you often need in manufacturing. But after 50,000 grips, but even to only 5,000 grips, that gripper is broken and you need to replace it. So that leads to or very costly repairs or a huge waste stream. And for example, Europe introduced the European Green Deal and even the right to repair. And that's also the reason why Apple has now their kits to be in front of that legislation, and that you're able to repair your own iPhone. But I doubt if we will all be able to repair such very complex products. So imagine a future where you don't need to repair your devices, but where the system has the ability itself to repair itself. A bit similar, like we're able to repair wounds and fractures. We're not over-dimensioned. If we have an exceptional load, we are damaged, but we can repair ourselves. And so that's exactly why we work together with material scientists in order to develop self-healing robots. So often there is a wide variety of self-healing materials, but often the faster they heal, the weaker the material is, because they have weaker chemical bonds. And so we use a certain Diels-Alder bonds, which is a very strong material. We can give the material very rich properties, from making it very stiff to very elastic. We can make the conductive, so we can embed sensors in it or even heating elements. But here you see that we were able, and this is patented material, to heal wounds in seconds. And of course, here the stresses on the material are not very big. If we do more severe damage, then it takes for this material 7 days to heal completely. But even now we're further pushing the limits. So here you see we damage a material, we connect it again, and after a few seconds, the material is strong enough to lift up a bottle. So one of the things, thanks to the, again, multidisciplinary collaboration between different parts, I'm sorry, I forgot a slide. So I think it's very important to think of more sustainable robots, and sustainability in our material is over different cycles. So first of all, if there is damage, we can extend the lifetime by self-healing and reusing it. If the system is not needed anymore, or too serious damage, in contrast to the human body, we cannot grow material, then we can recycle the material, which are or mechanically, so we can print, for example, but we can also do molding and extrusion and so on. New other fingers, for example, or a complete other purpose of the same material. We can also recycle it chemically. So that means we can, at that moment, make different material properties out of it, more stiff material or more elastic material. Moreover, we're looking if we cannot use renewable resources, biomaterials, and anyway, material will get lost in the environment. So that's why we're investigating biodegradation of the material. So if we lose material, it doesn't hurt our environment. And so thanks to the multidisciplinary collaboration, we can innovate. Yes.
We have to round up.
Yeah, I'm almost done. So
okay,
we do
perfect.
the complete value chain, from materials, the production, to sensors, to building the soft robots. And this is thanks to a very big team. And so it's not my work, but the work of a lot of disciplines, not only engineering, AI group, and so on, the electronics group, but also the human, the medical, and the social sciences. So as a conclusion, human-robot collaboration for complementary strengths, for both economical opportunities, but also societal challenges. And I think the way to face this is by very multidisciplinary teams. And so I also wrote a report for the European Commission about also legal aspects of human-robot collaboration that you can download here.
Okay, thank you.
Thank you.
Thank you for your presentation. I think the sustainable robots are really, from the design part, the future. So that would be really nice. I don't see any questions in the Zoom chat. So if people have questions, you can still write your questions there. A question that I have, because the trust that humans have towards robots, you told us that in the Audi factory, the humans really trusted the robot, the cobot. But what do you think is really important that people trust robots? Because, for example, people trust a fast driving train and can really stand there and wait for the train. but they are still afraid of robots. So what do you think is really important to make people trust robots?
Yeah, so that's why from the very beginning, we didn't develop the robots in the lab and impose them at the manufacturing line, but we did several tests where we brought in the Baxter robots and we did the Wizard of Us tests, like how you see collaborating with robots. Hey, what are your fears? How you see it beneficial? What about the privacy issues? Because of course we monitor the worker to make it more ergonomical, to which type of interactions you want, because we use gestures, but that is existing in the labs, but they're using gloves, which can be dirty, the new gloves clean. And so there are a lot of practicalities which make, how does it work on the real production floor? And that's why we really wanted to have tests. And so the robot was active for more than a year on the real production floor. The reason they stopped it was because they changed the model and they still need to find a new purpose for the robot in the Atron, but that had to go very fast. So I think trust is really interacting with specialists in it, not only engineers, but including sociologists who are trained to interact with the end user in order to gain their trust and not imposing technology on them.
Okay, thank you. I think we can go to the next speaker, or if someone else has another question.
I can also add it in answer it during the next presentation.
Yeah, so we can go to the next presenter maybe, and then if you still have questions, you can type it in the Zoom chat, and then Bram will answer the questions there.
Thank you.
Thank you.